So on belt and pulleys, the first part we will be looking at belt drive. So basically we have open and cross belt drive. Okay, so belts or ropes are actually used to transmit power from one shaft to another, okay, by means of pulleys which rotates at the same speed or at different speed. So this is an open belt drive. So from the diagram, you can see we have two pulleys. One is known as the driver pulley and the other is the driven. So basically, okay, when you refer to this diagram, the driver pulley is smaller and the driven pulley is larger. Okay, so now the smaller pulley has a radius of R1 and will be running at a speed of omega 1, while the larger pulley or the driven pulley is having a radius of R2 and a speed of omega 2. So when we refer to the belt here, which runs over the pulley, when the pulley rotates at different speed, let's say omega 1 with the smaller pulley and omega 2 with the larger pulley, we have belt speed. Okay, this belt speed is actually the tangential speed of the belt. Okay, so based on pulley 1, this is driver pulley or pulley number 1, we have a tangential speed or velocity of R omega. So which is R1 omega 1 with respect to the driver pulley. And for the driven pulley, okay, we also have a tangential speed of R2 omega 2. Now, since there is only one belt that is over both the pulley, so we can generally say that the V1 should be equals to the V2 based on one single belt. And then from the center of the first pulley to the center of the second pulley, the distance between them is called the center to center distance and usually is denoted by the symbol of X. So basically from here, what you need to know is, okay, a driver pulley, driven pulley, the tangential speed of both the pulleys should be the same even though they are running at different speed. And then the center to center distance X. So theta here, okay, is called the angle of lap or the angle of wrap. So both the theta from the geometry of the figure, both the theta must be the same or equal. So what is angle of lap or angle of wrap? So when you refer to the smaller pulley, as you can see, the belt is lap or is running over the pulley at this point, from this point here to this point. So at these 2 points, at both the points, you can see the belt is about to leave the pulley at both these points where it touches, the belt touches the pulley. So the angle of lap or the angle of wrapping is when the belt is in contact with the pulley. So this is the theta or the angle of lap. So the introduction. Belt or ropes are used to transmit power from one shaft to another by means of pulley which rotate at same speed or at different speeds. The amount of power transmitted, okay, so the power usually will be transmitted from driver to driven, okay, from the smaller pulley to the larger pulley. So The driver, this we have chosen the smaller pulley, and the driven is the larger pulley. You can change or you can alter this. Okay, you can have larger pulley as driver and the smaller pulley as driven. Not necessary that the smaller pulley is always the driver. Okay, so it depends on whether you want to increase the speed of transmission or you want to reduce the speed of transmission. Okay, so when a smaller pulley drive a larger pulley, actually the speed, okay, is being reduced. But then when you refers to larger pulley, if larger pulley to be the driver and the smaller pulley to be the driven, then we say speed to be increased. Okay, so not necessary that the smaller pulley is a driver. Okay, it can be the driven. So now these are the 4 important factors that affect, okay, the amount of power to be transmitted from the driver to the driven pulley. First, the velocity of the belt, that is the tangential speed. Okay, both V1 and V2 must be the same. Okay, even though the rotating speed omega 1 and omega 2, they are different. Because we are using only one single belt which is lapping over both the pulley. The second point is the tension under which the belt is placed on the pulley. So in this case here, when you look into the diagram, when you look into this animation here, you can see that pulley here is rotating in anti-clockwise, and it also will affect the rotation of this driven pulley to be anti-clockwise for an open belt drive. So what happened is the smaller pulley here will exert a pull at this point. Okay, take a look at this laser pointer here. It will exert a pull at this point here when it rotates in anti-clockwise direction. So what happened is the belt on the upper side here will be subjected to tight, okay, pulling. Okay, the belt on the top here, on the upper side, will be subjected to pulling and then being delivered to the lower side of the arrangement. So therefore, we say that the tight side appears here on the upper side and the slack to be at the lower side. So we have tight side tension, okay, in this case, and slack side tension here. So tight side tension usually is denoted as T subscript 1. Slack side tension is denoted as T subscript 2. So T1 usually refers to tight side tension. T2 usually refers to the slack side tension. And always the tight side tension is greater than the slack side tension. So the amount of power transmitted also relies on the tensions under which the belt is placed. Okay, and then the third point is the arc of contact or the angle of wrap, WRAP, or the angle of lap, which is theta. So when theta is increased, it means that the surface contact between the belt and the pulley also increase. When the theta, I repeat once more, when the theta increase, the contact surface between the belt and the pulley also will increase, and that indirectly will increase power transmission. The fourth point is the condition under which the belt is used. Usually the belt and pulleys are used in dry environment, okay, in drier environment. So because friction is very important, okay, in this belt and pulley drive, because it needs a gripping force between the belt and the pulley. So when the gripping force is increased, that means the amount of power transmitted will be more, whereas the slippage, SLIP, okay, is reduced when the contact surface is greater or when the angle theta is greater. This also can be increased by placing what we call jockey pulleys or idle pulleys on the belt, either on the upper side or the lower side. Now we come back to this. If let's say, for example, the pulley is rotating in clockwise direction, but what I've shown you here, they are rotating in anti-clockwise direction. What about if let's say it rotates in clockwise? Okay, so when the smaller pulley or the driver pulley rotate in clockwise, the larger pulley, of course, also will be rotating in clockwise. So when it rotates in clockwise, it will exert a pull at the lower portion here. Okay, the lower side of this is the assembly. Okay, so it will exert a pull here, which causes tight here at the bottom and deliver the belt to the upper side, which we call the slack. Okay, so it depends on the direction of rotation of the smaller pulley. So theta is called the angle of lap or the angle of wrap, which is converted to radians, usually being converted to radians by theta over 180 times pi. You can also take it as 360 here, but here you have to multiply by 2 pi. Okay, so V1 or V2 here, the V1 or the V2, they are called the belt speed or the tangential speed. We know that tangential speed is usually given as R omega, where R refers to the radius of the respective pulley, and omega, it refers to the angular speed of either shaft. Okay, so let's say, for example, you are referring to the smaller pulley, then you will have subscript 1 for the radius, and subscript 1 for the rotational speed. Okay, so since the tangential speed for both pulleys are the same because of the belt speed, so we can work out, okay, the speed ratio between the smaller and larger ones. So what you need to do is you just substitute your R omega. V is the tangential speed, right? So you substitute your R omega for both the pulleys, which you have R1 omega 1, R2 omega 2. You can also directly change it to diameter and here to diameter. We know that radius is equals to diameter over 2. So you can put diameter over 2 here, diameter over 2 here. So when both sides, okay, when you look into the equation, you have over 2 and over 2 here. The both sides of the denominator with the 2 can be cancelled off. So that is why you have diameter. Or the omega, you can also put 2 pi n1 over 60. And 2 here, 2 pi n2 over 60. So the 2 pi, where the 2 pi and 2 pi on both sides, and the 60 and 60 on both sides cancel off. So that is why you can come to this sort of equation. So when you rearrange this, you have d1 over d2 equals to n2 over n1. So from this equation, it gives us the knowledge that, okay, when the diameter, okay, is larger, then the speed might be lower. Or when you refer to smaller diameter, the speed might be higher. So you can see the diameter and the speed, they are inverse. Larger diameter, lower speed, and smaller diameter, higher speed. From this relationship here, you will be able to know or express between the diameters of rotating components with their respective speed. Inverse. Now, for open belt drive, this is an open belt drive again. So what I need to explain is how to define the power transmitted that is going to be transmitted by either open belt or cross belt. Later on the next slide, we will be looking at the cross belt drive. So, but for both cases, power is defined as force times velocity, the power transmitted by the belt and pulley system. So this force here usually refers to the effective tension. That means based on the tension on both sides. So if this is rotating in anti-clockwise direction, this tension here, this should be T1 tight side. And the tension here on the lower side here, when it rotating anti-clockwise direction, this should be T2 slack side. Slack side will be minimum, tight side will be maximum. So the force here usually refers to the effective tension, means the difference in tension between the tight and the slack. So you can take the force as T1 minus T2, where T, the uppercase letter T, stands for tension. And then the velocity here can be referred to the belt velocity, either V1 or V2 will do. But then make sure when you consider V1, it must be R1 omega 1. And then when you consider this as V2, you must consider R2 omega 2. You cannot take V2 and then put there R1 and this as omega 2. Cannot. Okay? So the effective tension is given as the tight side minus the slack side. That means the maximum tension minus the minimum tension multiplied by the belt velocity, which is R omega, and multiplied by this N. This N here is the number of belts. Okay, the number of belts in the belt and pulley drives. So T1 refers to tight side tension, should be here. Okay, when this rotate anti-clockwise. When this rotate clockwise, your T1 should be here. So in this case, it's anti-clockwise. So your T1 should be here, your T2 at the bottom here. Because when it is rotating anti-clockwise, it exerts a pull here. When it rotates clockwise, the pull is here. Okay, so basically the T1 will change depending on the direction of rotation of this driver pulley. So T1 is the tight side tension and T2 to be the slack side tension. So T1 tight side tension can also be called as the maximum tension. T2 can also be as the minimum tension. And the V is your belt speed or the belt velocity or tangential velocity, which should be in meter per second. Both of these tension should be in Newton. Okay, Newton and Newton. Tension is a force. Okay, so belt speed is meter per second and it can be found by taking R omega. The R and the omega with respect to the pulley that you refer. Okay, so both the pulley will give you the same belt speed. So N refers to the number of belts. So now, what about the theta or the angle of lap? So if you want to find the angle of lap or the wrap, okay, you can basically take this triangle that I have drawn here, basically from point O, okay, you draw a straight line, okay, which is parallel to the line of the belt which we have drawn geometrically. Okay, so this line here, O to A, must be parallel to this belt here, okay? And then you have the center to center distance, which is X. And then this length here, this length actually can be found by taking the radius here, R2. This should be radius R2 minus the radius R1. Okay, minus the radius R1. So you have R2 here minus R1. So you have this length as R2 minus R1. Okay, or uppercase letter R minus lowercase letter r. That means the larger minus the smaller one. And then this angle here, now the whole angle here is theta. So half of this is some sort of like a rhombus, okay? So, or kite, sorry. Then you have theta, the whole angle here as theta. So half of it should be theta over 2. So based on this, which we call the adjacent side, and this should be the hypotenuse side, which is opposite to the 90 degree. Adjacent and hypotenuse, you should have cos of this angle. So cos theta over 2 should be equals to adjacent divided by hypotenuse. So if you want to find theta, that is the angle of lap or wrap, then you have cos inverse, then you have 2 times cos inverse of this. You will be able to find out the angle of lap or wrap for an open belt drive. If let's say you want to find the length of the belt, okay, then you can refer to this formula here. Okay, where R is referred to the larger radius. The R here refers to the smaller radius. Okay, X refers to the center to center distance. So this is the formula that we use to find out the length for any open belt drive. Then the next we goes to, okay, cross belt drive. So for a cross belt drive, this is how it looks like. Okay. So here in this case here, the smaller pulley, which is the driver pulley now, is rotating in clockwise direction. So when it refers to clockwise, and this, okay, here would be the angle of, which will be the contact point. So when it rotates clockwise, so it will exert a pull from this side here. The pull from this. Okay, so this should be the tight side, and this should be the slack. Now, if it rotates anti-clockwise, then your pull should be here, and the tight side should be on this belt here. Okay, so I hope you all understand. If you have any questions, you can still ask me. Okay, always welcome. So, if we want to find the angle of wrap, okay, the angle of wrap, okay. Now, in this case here, should be your theta. The whole theta should be here, yeah. I put opposite, okay. So theta over 2, okay, should be this angle here. Your wrapping angle is from here to here. So don't care about theta or alpha because these are only symbols. Now the most important thing is we have already know what it means by wrapping. W-R-A-P, wrap, that means cover, okay, wrap, okay, over a certain amount of surface we call wrap. Okay, so this will be your angle of wrap, this case here, which is alpha. So remember, what we need is angle of wrap, not this angle here. This time is this side here, which is the alpha. Okay, so what we need to do is you can draw a line, this line which I've drawn in dash, okay, from the center of the smaller pulley. And then the line that which is being drawn here should be parallel to this. And then from there, you go to the center of the larger pulley. So from this, we will be able to say that this length here, this must be 90 degree. Of course, this must be 90 degree here. So this length here is your R1. This is radius R1. Okay, from here, you look at my pointer. This should be your radius R1. And this should be a radius R2. So the total length should be R1 plus R2 here, with the length here as X, and this should be 90 degree. This should be 90 degree. So this angle which we have is theta over 2. This length is X, and this length here is R plus R. So again, we apply the cosine rule, the cosine, okay, of adjacent over hypotenuse. So remember, the angle of wrap is alpha, not theta, yeah? So you have this. So what we need to do is we find out theta first. Okay? So we have theta is equals to 2 cos inverse of R plus R over X. So once we have found theta, theta is this whole thing here. Okay? We can say theta is this whole thing here. So if I want to find alpha, so I need to take the complete angle of a circle, which is 360 degree, minus of this portion here. So I get this angle of wrap alpha. Okay, so this would be your angle of wrap, this case for cross belt drive. Okay, so in case if you want to find the length of a cross belt, so you can use this formula that I've given here. Okay, that's all, and thank you very much. Stay safe. So the part 2 of belt and pulley drive. So this part, we will be looking at the centripetal and centrifugal acceleration. Actually, centripetal and centrifugal, they are the same. The only thing is centripetal is a force which is acting towards the center of rotation, and centrifugal is a force which is acting away from the center of rotation. So by Newton's third law says that every action there should be an equal and opposite reaction. So there is an action, then there should be a reaction. Okay. So since the belt continuously runs over the pulley, therefore, okay, some centrifugal force is caused, okay, whose effect is to increase the tension on both sides, tight as well as the slack side. That means the T1 and the T2. So the tension caused by the centrifugal force is called centrifugal tension. At lower belt speed, let's say less than 10 meters per second, the centrifugal tension is too small, but at higher belt speed, that is more than 10 meters per second, its effect is considerable and thus should be taken into account if it's greater than 10 meters per second. If it is less than 10 meters per second, we can neglect the centripetal or the centrifugal tension. So when the belt continuously runs over the pulley, actually it exerts a pull here, acting outwards. Acting inwards is called centripetal. Acting inwards is centripetal. Acting outwards, you can call it as centrifugal. Actually, centrifugal and centripetal is to be the same. So what happened is it actually tightened, okay, the tension on the tight side as well as on the slack side. Okay, so you assume a very small portion of the belt, which consists of a mass M, mass of belt. Okay, actually it produced a quite considerable amount of pulling force, which is acting outwards. Okay, we only take into account if the belt speed is more than 10 meters per second, not less than 10 meters per second. Okay, and usually the centripetal or the centrifugal tension, is denoted by the symbol of T with a subscript C. So TC, that is the centripetal or centrifugal tension, can be found by mv squared, or mr omega squared. Okay, or mr omega squared. Or it can be found either by using rho A. Rho is the density of the belt material. Rho is the density of the belt material. It depends on what type of belt you are using, leather belts or others. Okay, if leather belts, the density should be approximately 1000 kg per meter cube. So this A here is the cross-sectional area of the belt. So it depends on you are using flat belt, okay, rectangular cross-section, rope or circular belt where the cross-section is circle, okay, or a V belt which the cross-sectional is some sort of trapezium, okay, a trapezoidal cross-section if it is a V belt. So mass actually can be found, this M actually is equals to rho A, where density is kg per meter cube and the area is meter square. So you can find out the mass of belt, which is in kg per meter length. So for belt, for any lengthy object, any object has a considerable length, the mass is always measured as kg per meter. Okay, kg per meter. So this mass here is kg per meter and it is not kg. So rho, which refers to the density of the belt materials, which is in kg per meter cube. Okay, remember that only when mass or density of belts being taken into account, and in certain cases when the velocity of the belt is greater than 10 meters per second. Okay, then only we will take TC into account. So if, let's say, for example, when we are solving problems, when mass or density, they are not given, or let's say the belt velocity is less than 10 meters per second, then we won't take TC into account. Unless mass or density or the speed is greater than 10 meters per second, then only TC will be considered. Now, the next term here is what we call the initial tension. Now, tight side tension is denoted as T subscript 1. Slack side tension is denoted as T subscript 2. Centrifugal tension or centripetal tension is denoted as T subscript C. Initial tension is denoted as T with a subscript O or 0, the symbol that we use. So initial tension, which is also known as static tension or average tension. So from the definition here, when we say average tension, that means you are taking average between T1 and T2. So for initial tension, you usually take T1 plus T2 over 2. Okay. Now, tension which is applied to the belt. Okay, you apply a pulling force on the belt when you are placing initially at the start. You are placing the belt on the pulley. You are mounting the belt onto the pulley. So you have to apply an initial pull, which we call the initial tension. That is T0, which is T1 plus T2 over 2, which is the average tension. So now we have T1, T2, TC, and T0. Okay, so I hope you remember all these symbols that we use in this part of your machine components design. Now the next is the belt tension ratio. So from the word ratio, okay, when we look at the word ratio, it can be something, a quantity, a maximum quantity divided by a minimum quantity, or a minimum quantity divided by maximum quantity. It always gives you a ratio of same units, or same quantity. Okay. So in this case here, we have open belt and cross belt. So both will give you, or we will be using the same belt tension ratio. It's the same belt tension ratio. So there are certain categories that we have to obey or look into, okay, to consider what formulas to be considered when we want to find belt tensions, either T1 or T2. So this is your open belt drive, and this is the cross belt drive. So for flat belt means the cross section of the belt, when you chop this, or we cut it, and then you look from the side, okay, it gives you something like this in section, which we call a rectangular cross section. This is for flat belt. Okay, so the area is just the width of the belt multiplied by thickness. Okay, so in case if you want to consider TC, or you want to consider the stress, okay, due to the tension on the belt, the stress due to tension on the belt. So we know, we have to remember that stress is always defined as force over area. Stress is defined as force over area. And the force that we consider is always the maximum tension, which is the T1. Okay, or even when you want to consider find TC, so you need to know the area. So it depends on whether you are using a flat belt, a circular belt, or a V belt. So a flat surface. Now, flat belt always comes with a flat surface pulley without any groove, on the pulley, on the surface of the pulley for flat belt. But then, of course, you can also use a V groove for a flat belt. But then usually flat belt is used with flat surface pulley, but the slippage is very high. It actually also depending on the surface in contact between the area and the pulley. Okay, so the belt tension ratio, if let's say we are looking at a flat belt, then we will be using T1 over T2, that is maximum tension over minimum tension, which is equals to exponential, this E is exponential, mu theta, where this mu is the coefficient of friction and this theta here is the angle of lap or wrap. So when you apply theta into this formula, make sure your theta is in radians and not in degree, in radians. So you must convert theta degree to radians by dividing it with 180 times pi, or divided it by 360 times 2 pi. Okay, so this is the belt tension ratio for flat belt. So if let's say we take the mass of the belt into account, okay, let's say the mass or density is given, okay, or let's say the belt speed is greater than 10 meters per second, then we have to include the centrifugal or the centripetal tension. So the belt tension ratio is usually given as what I have written here. So to prove this formulas here, we must apply geometric series, okay, the series, okay, which to derive both these formula, which is not necessary for your level. Now, if let's say, for example, if we are using a circular belt, a rope, or a V belt, then we must have a V groove pulley. That means the surface of the pulley here, you must have a groove on it so that the circular belt can sit nicely on the groove, or the V belt can sit nicely on the V groove on the pulley, the side surface of the pulley. So this angle 2 beta is called the groove angle. 2 beta is called the groove angle. Okay, and these two surfaces will give you a friction. Okay, so actually when it refers to V belt, okay, the contact surface between the pulley and the belt is greater now. So the power which can be transmitted should be higher because of the contact surface. So if let's say, for example, V belt or circular belt, then to find the belt tension ratio, we must use this, okay, which is T1 over T2 exponential mu theta, the same on top. But then you have to include cosecant beta over 2, where beta here is actually, this should be beta, yeah, not 2 beta, the angle, the groove angle of the groove pulley. Okay, this should be beta, not 2 beta. Okay, so if we take mass into account, this is without mass, yeah. So if we take mass into account, that means we apply this formula again, but then right here we put cosecant beta over 2 here. Okay, so you can see this formula when mass is taken into account, so where TC is included. Okay, so this basically will give you a general, okay, idea, okay, what belt tension ratio to be considered when we solve problem on belt tensions or belt and pulley drives for machine components design. So the next part is to look into what is the maximum or the ultimate, that means the greatest, most power that can be transmitted by a belt pulley system. So maximum power transmission. So we have to take note when we solve problems. Okay, the problems should not have given us any belt speed or tangential speed or pulley speed. The question must not have given us any of this. The second thing is the mass or density of the belt is taken into account. So that means TC is being taken into account. And then in addition, the question asks for ultimate power transmission, greatest power transmission, or maximum power transmission. So if these three categories are fulfilled, then you can use the following formulas that I will be showing you here. So first thing is formula for power transmission. So to find any maximum or minimum value, we must differentiate the power with respect to the speed or the velocity. Okay, so when we differentiate this, or you can rewrite this by including the TC, so you have something like this. Okay, or you change your T2 into something in terms of T2 minus TC into something of T1 minus TC, then you can make use of your belt tension ratio, which you have this. Okay, then simplifying that, you got to something like what I have shown you here, where your TC is given as rho AV square. Okay, AV cube, sorry, this time, where you you multiply your V from here to this, so you got V cube. So what we're going to do is we're going to differentiate this formula with respect to V by applying your differentiation application. If you want to find any maximum or minimum value, you must differentiate an equation with respect to its variable, then equate it to 0. So in this case, velocity would be the variable. So you differentiate P with respect to V here. Differentiate the P here with respect to the V here. So once you do that, okay, so you will have something like this. Once you differentiate this equation by using product rules, and then after that you equate this to 0, you will get something like this, which T1 equals to 3Tc, where Tc is equals to rho AV squared. So 3Tc. So let's say, for example, if I want to find Tc based on this condition, so I can take T1 over 3. So you cannot find Tc by taking T1 over 3 in all the cases. Now you can only use a formula of T1 over 3 to find your Tc, unless this is thick, this one is thick, and this one is thick. Okay? So you can have your Vmax now, Vmax to the power of 2, or you can have Vmax equals to square root of T1 over 3 rho A by substituting your 3 rho A back into the equation for your V. Okay, so you will have your T1 over 3 rho A square root, where you have your Vmax. So once you have your Vmax, you can find out your power max by substituting your Vmax here. Okay, and also you can find out your Tc by taking T1 over 3. Okay, so that's for this section. Thank you very, very much. See you.